Hello, my name is Micheline Soley, and I use blue waters to simulate an ultracold inferno. So more specifically, what I do is I study the ultracold potassium rubidium dimer reaction. So what happens is in this reaction is you have two potassium rubidium dimers, so each is KRB. So the two KRB come together at 300 nanokelvin, so extremely cold. And then when the four atoms come together, they release a lot of energy, so it's 4,000 Kelvin hot, and the atoms start moving around chaotically. And then only when they can organize themselves into two pairs of new molecules, K2 and RB2, can they finally escape as product molecules. And these product molecules are quite cold, they're 14 Kelvin. So what we want to do is we want to make it possible to simulate product formation from the four atom complex. And in order to make this happen, we have to recognize that the reaction acts as a kind of ultracold inferno. So the problem in simulating this reaction is that typically when people look at ultracold reactions, they use quantum mechanics, because quantum mechanics are very exact and includes quantum effects such as quantum tunneling or interference, like you might see in a double slit experiment. But there's a problem with this, because if you're trying to simulate something quantum mechanically, specifically exactly with what's called time-dependent quantum mechanics, it's very expensive. So time-dependent quantum mechanics is a nice way of simulating something because it gives you like a molecular movie of what's happening. So you can see what's happening to the atoms at time step by time step. But it's also extremely computationally difficult, and it becomes impossible for large or very cold systems. So one of the largest reactions that's ever been studied with time-dependent exact quantum mechanics is this reaction here, H2 plus OH. And this is a reaction that's important in combustion. So if you think here we're working about in ultra-cold chemistry, and this technique has only been used for combustion, we have a problem. So what's the origin of this problem has to do with the scaling of quantum mechanics. Because quantum mechanics it can be, for example, you can do it with grid methods. And grid methods become really expensive when you're looking at very cold temperatures or high dimensionality. So specifically, as the temperature decreases, the size of your grid increases. And this happens inversely with the square root of temperature. So as you get to ultra cold temperatures, it becomes extremely expensive to simulate. And in addition, we have what we call the curse of dimensionality, which is as you increase the complexity of the system and you go to higher dimensions, the scaling increases exponentially. So it becomes, currently people haven't been able to do it with systems of more than 4 atoms, and they were very hot systems. So we need to find a way around this limitation. So one way that could be a way around this limitation is classical mechanics. So classical mechanics you can do without a grid, and it's free of that kind of exponential scaling. But the problem is classical mechanics doesn't include quantum effects, like interference. So typically, classical mechanics is done at very high temperatures. So people would think that typically you can't use classical mechanics for ultracold reactions, that ultracold reactions would just be quantum. But what we realize is that the KRB dimer reaction can be seen as what we call an ultracold inferno. So the way that you see this can be shown as on the picture on the left. So the picture on the left is a potential energy surface that shows the forces that are acting on the two product molecules, K2 and RB2 with distance. So the y-axis is showing the amount of energy, and then the x-axis is showing the separation between the two dimers. So when the two dimers are very close, you have a collision complex that's 4,000 Kelvin deep. But when the two molecules finally separate to form products, it's only 14 Kelvin. So even though this is magnified on a large projector screen, you can only see the difference in the product energy by zooming in 10 times. So you can see the huge scale and energy difference. But even though there's this huge scale and energy difference, you can actually use it to your advantage because you can use it to make simulation of reaction possible that might not otherwise be possible. So the way that we use that is that we force classical mechanics to work together with quantum mechanics, whether it likes it or not. So what we do is we treat the hot part, the 4 atoms in the collision complex, classically, and then we treat the cold part, the products, quantum mechanically. And then we have a boundary between the two. So the way that we do this more specifically is that the hot part is simulated with semiclassical mechanics, which is a kind of approximation that's between quantum and classical mechanics. And so the way that we study the inner region is we want to know how many different configurations of the 4 atoms can be accessed. And quantum mechanically, this would be a very expensive problem, but classically or semi-classically, it's not so expensive. And the way that we reduce the cost of this is through Monte Carlo integration. So what we do is we sample the different configurations of the atoms, and then we decide whether those configurations of atoms are allowed at a given temperature. And so we take the ratio of the ones that are allowed to the total amount of space sampled in order to get a sense of how many different configurations are possible in Monte Carlo integration. And in order to make this more computationally effective, we use blue waters and data parallelism to simulate the Monte Carlo integration. So instead of having one single core look at all of the different possible configurations of the atoms, we spread the different tests along different cores. And so in this way, we can actually simulate quintillions of sampling points effectively and very quickly on blue waters to get a well-converged integral for the number of different possible configurations of atoms there are. So that's the hot part, done semi-classically. Then we have to move to the cold part. So to do the cold part, we use a combination of 2 different techniques. One is random matrix theory, and the other is R matrix theory. So they're both clever ways of, instead of having to do the full 6-dimensional problem that would be very hard to do quantum mechanically, you can do it in just 1 dimension. And so the way we do this is we take the number of different configurations that we calculated classically, and we use that as a parameter for a random matrix. And that random matrix is full of random numbers, but it gives us the kind of statistics that we would expect for a system with a certain number of possible configurations. And then we feed that random matrix into R matrix theory, which is a way of finding out the final scattering of what kind of products are formed in the reaction and what their rates are, and in what kind of product distribution the rates lie, the different product states lie. So, but the problem with R matrix theory is that at times the bottleneck to R matrix theory has been the inversion of the R matrix, because it can be a very large and non-sparse matrix. So blue waters is helpful for us in that as well, because it allows us to use parallelized matrix manipulation software like Scale APAC in order to do larger matrices than would otherwise be possible. So we've started already running this on blue waters, and it's shown that using semi-classical mechanics can give us a way to simulate what might not otherwise be simulatable in the hot region. So here, I'm looking at a simplified model of the inner region, of the hot region, called rigid rotors. And I'm looking at what the semi-classical answer we calculate is compared to what we would get if we solved it exactly quantum mechanically. And then also if we compare it to an analytical value calculated mathematically. And you can see that all of the numbers agree fairly closely, which suggests that semi-classical mechanics is an effective way of calculating the value in the hot region, and that you also get agreement between the classical and quantum mechanics in this region as we expected. And this is important because it's important for several reasons. One of them is it makes it possible to calculate reactions that might not otherwise be calculatable by bridging together these classical and quantum worlds that are often thought of separately. And also by seeing something in a classical picture, you can, instead of tracing what happens to waves, you can instead think about how particles are moving. So it gives us a more intuitive explanation of how the reactions happen. And in addition, what we find is that even though people tend to think that ultracold reactions are quantum, we found that actually through semiclassical mechanics, you can actually see that in many ultracold reactions, there are elements in which classical and quantum mechanics will actually agree, that classical mechanics will be exact and produce the right answer. So this has a broad impact to a variety of fields. So most directly, it gives a tool to the ultracold theoretical chemistry community of how to look at these reactions. And it also helps, it gives us information that we are going to use with our collaboration with an experimental team that's currently working on this reaction. But more generally, by finding out this quantum classical correspondence, it's a tool that can be used throughout computational chemistry for reactions at other temperatures as well. And in the end, ultracold chemistry also has applications to a variety of fields, such as investigation of fundamental constants or quantum computers. So it has a possibility to impact a wide range of fields outside of the ultracold and theoretical chemistry communities. And I'd like to thank the Blue Waters for the Blue Waters Fellowship and all that it's allowed me to do with this research, for the education opportunities it's given me to learn supercomputer techniques, as well as computational support and resources that wouldn't otherwise be available to me, and also for the opportunity to discuss with researchers from other fields. And I'd also like to thank my advisors and our collaborators, the Blue Water Project staff, the Blue Waters Fellowship, and the NSF Fellowship, and you for your attention. Thank you.